Okay, great. So today we're very much delighted to be hosting Dr. Nandini Hazra, and she's a postdoc at the moment in NCPJ, and she obtained her PhD here in Italy in GSSI, and she's also a part of the Einstein Telescope Consortium. Her expertise are basically multi-messenger astronomy, and she's working on galaxies for LSST Rubin. So yeah, today she's got like so many exciting things to share with us, and we're very much looking forward to your talk. Please go ahead. Take it away.
Thank you, Fatima. I'll just share my screen real quick. All right. Can you see my screen?
Yes.
I'll just move to... Great.
Perfect. You also see the cursor.
Perfect. So let's... One second. All right. Let's go. Hi. Good evening, everyone. Thank you, Fatima, for that wonderful introduction. I'm Nandini Hazra. I'm a postdoc at the National Center for Nuclear Research, NCBJ, in Warsaw, in Poland. And I would like to share with you some results that we've obtained in the last couple of years, focusing on the synergy that we could have in the future between Rubin and the Einstein Telescope, and sort of the multi-messenger picture that we could expect in the next era of the third generation of gravitational wave detectors. I would like to mention that this work has been done along with Eleonora Lofredo, Marica Branchesi, Uliana Duplezza, Jan Harms, Samuele Ronchini, Filippo Santoliquido, and a bunch of other people whose names did not fit on the slide, but they have all been instrumental and crucial for this work. So it was really a group effort, as well as with the Einstein Telescope collaboration at large. So with that, I will just jump straight into a short overview of the gravitational wave interferometers that we have currently, which is also known as the first generation of GW interferometers. So when we say first generation, what we mean are the four interferometers we have currently functioning, two in the USA. So that those are the LIGO detectors at Hanford and Livingston, the Virgo interferometer, which is in Kashina in Italy, and Kagra, which is in Japan. So these so together we sometimes will also call them the LIGO Virgo Kagra or LVK detectors, and they have been functional and detecting. At present, they have more than 200 detections of compact binary coalescences, and of particular interest has been the GW170817 detection, which was made in 2017 and is the first and only multi-messenger event that has been detected so far with gravitational waves. And it was detected in the LIGO Virgo interferometers, followed shortly by detections in the gamma ray instruments, as well as a detection by the SWAP supernova survey, which detected the optical counterpart of this BNS merger, of this binary neutron star merger, which was named the AT 2017 GFO. So this was a kilonova observation. Even the host galaxy of this event, NGC 4993, was identified, which led to a host of very interesting observations and measurements. And in particular, it led to the characterization and detection of a fast decaying blue kilonova accompanied by a more slowly evolving red component of the kilonova. And together they were observed by a host of other electromagnetic observatories, as well as the evidence of. So, firstly, what this established was that binary neutron star mergers were associated with kilonova emissions, and that the kilonova emission was also associated with the nucleosynthesis of heavy elements. So this was a very interesting result. However, the picture since then has been a little bit bleak, which is that only one other binary neutron star merger was observed in the third observing run of the LVK, which is named GW 190425. However, this BNS merger had a very large area of sky localization. So in spite of dedicated, extensive electromagnetic follow-ups, no EM counterpart was observed. However, this BNS in itself was very interesting because its total mass was higher than any BNS we had observed previously in the Milky Way. And however, since then, no other gravitational wave and electromagnetic events have been observed concurrently. And in particular, no other BNS mergers have even been detected in the fourth observing, which is the current observing run of the LVK. And this leads us to conclude that at present, BNS merger detections with current GW observatories are rare events. They are not routine astronomy. And joint detections of BNS mergers with kilonovae are even rarer events as a result. So moving on from the current generation of GW interferometers, what we will have in the second generation will be upgrades to LIGO and Virgo interferometers and the addition of a new interferometer in India called LIGO India. And together they will operate at an improved sensitivity in the early 2030s, and this will be the fifth observing run, which LVK will start once the current observation run, which has been slightly extended to overlap with Rubin, is concluded, and the engineering run happens after that. However, of particular interest to us for this talk are the third generation of GW detectors. So these will come online in 2035 and later. And in particular, I have circled here the detectors that we can expect to have. These are only the ground-based detectors that we're focusing on for this talk. So in Europe, we will have the Einstein Telescope. And in addition to the Einstein Telescope, we will also have the Cosmic Explorer, which is supposed to be one in the United States and one in Australia. The Einstein Telescope will be Europe's third generation GW detector. It was originally envisioned as a triangular underground detector with xylophone nested arms and having a high frequency component in addition to a low frequency cryogenic component, which would allow the PNS merger signal to be in the sensitivity band of the ET for a longer time. So ET, as I said, had been envisioned originally as a triangular underground interferometer, but this plan has somewhat been modified, and we will get to that later. ET has been part of the S3 roadmap since 2021 and is in the process of being the site selection is in progress, and we hope to have this detector in the mid 2030s and thereafter. Right. So, oops. Okay. So this is the sensitivity curve of the Einstein Telescope in comparison to other ground-based detectors that we will have in the second and third generation. And what we can see, as I mentioned, is that the improved sensitivity at lower frequencies of ET will allow the BNS signal to be in the band of ET for a longer time and therefore to be localized better using the imprint of the Earth's rotation. And this is crucial because it will allow us to detect many BNS mergers with a very good sky localization. In particular, what we are finding and what we expect is that we will have an order of 100 BNS mergers, which will be localized better than 100 square degrees, and an order of 10 BNS mergers localized even better than 10 square degrees, which is very interesting to us because Rubin has a field of view closer to 10 square degrees. And this is very interesting for us to have these numbers and to have these kind of statistics in that era. Right. So what do we need to do to capitalize this large wealth of information that we will be getting from ET in the next era? What we need to do, in particular in this instance, is to be developing dedicated target of opportunity strategies in order to follow up the BNS mergers and to observe the optical counterparts, in particular the kilonova transient, which is very fast moving and very faint. Right. And why do we need to develop target of opportunity strategies? So the cadence and exposure of LSST in particular is not suitable for fast evolving faint transients like the kilonova. And so even though, as we have seen in the last week, the wealth of alerts generated from LSST, we will detect a lot of supernovae and a lot of other solar system transients as well with the standard LSST cadence. What we have with the LSST survey mode is that we have 30-second exposures at a time in a single filter, and then imaging the same part of the sky once every 3 nights. However, this is not an ideal exposure and cadence for kilonovae, where if we go from one night, one epoch to the other, and have 3 nights in between, this allows us to lose a lot of the kilonova signal in the interim time. Plus, 30-second cadence gives us an exposure, which also is not ideal for detecting the faint kilonovae that we can expect to have. So this is study. There was a study in 2022, a paper by Igor Andreoni and collaborators, which estimated the serendipitous discovery rate of kilonovae using the standard LSST cadence to be of the order of 30 to 300, where only about 10% of them would be characterizable as kilonovae transients reliably in the whole 10-year run of LSST without TO observations. And this is also because a large fraction of the kilonovae will be lost, as I mentioned, with just 30 seconds of exposure. At present, there are target of opportunity strategies in play, which are being refined as we speak and are being tested and are being implemented. And these are going to be crucial for the 6-month overlap that Rubin will have with the LVK run later this year. And in this kind of effort, which is being led at present by several members of TVS, and in particular by Sean McBride and Shreya Anand, where BNS merger triggers are, we hope to follow them up. And BNS merger and neutron star black hole merger triggers are hoped to be followed up based on their area of sky localization. So gold events, which should be localized within 100 square degrees, would be observed over several epochs, starting with the 3-filter strategy and then with the 2-filter strategy, whereas silver events, which are localized within 500 square degrees, will have only 2-filter strategies with a slightly lower exposure. And this is because Rubin's wide field of view of 9.6 square degrees, the extremely fast slew, is ideal for covering large areas of sky localization, which we expect from the GW interferometers. In addition to that, this wide filter coverage from Rubin allows us to also observe the color evolution of the kilonova over the first few nights. And moving from the LIGO Virgo set of alerts to Einstein Telescope will be a different set of considerations, and it will be a game changer for us, because instead of having very few BNS mergers, which at present has been 2 BNS mergers detected over the last 9 years, instead we will have an order of 10 to 100 BNS mergers detected per year, and therefore we need to have a paradigm change in how we do TO follow-up as well, to follow up, to reach deeper sensitivities, ideally with longer exposures, and therefore be able to catch also distant kilonovae, and therefore capitalize on this really better localization capability that is provided to us by the Einstein Telescope. So right now, I will talk about these Rubin and ET synergies. I've spoken so far about why this is important and why we should be interested in the era where Rubin and ET will work together. Now I will talk to you about the Rubin ET synergies through the lens of 2 particular works that we have explored. The first was this detector design study that we did with a lot of members interested in the Einstein Telescope and from the Einstein Telescope collaboration, where we evaluated the different designs proposed for the Einstein Telescope through the lens of multi-messenger astronomy. And this is a snapshot of the paper, which was published a few years back in 2023. And what this paper focused on was in evaluating what the different proposed designs of the Einstein Telescope would do for the science that we can expect with the Einstein Telescope working in synergy with electromagnetic detectors. This was only one of the science cases, but that's the topic that I'm going to talk about today in this talk. So firstly, 2 different detector designs for the ET were proposed. One is a triangular original idea that was envisioned. And the second were the 2 L-shaped interferometers, where one would be placed in Sardinia and the other would be placed in the Euro region. However, it was not very clear what the science benefits of one configuration over the other would be, and therefore this was something we studied extensively. We also explored what the science advantages would be of having the full sensitivity of the Einstein Telescope in the high frequency and the low frequencies, versus a worst case scenario where only the high frequency component of the Einstein Telescope can be achieved. In addition to that, we also explored different arm lengths for each of these interferometer configurations, where we explored 10 and 15 kilometer arms for the triangular design and 15 and 20 kilometers for the two L-shaped designs. The two L-shaped interferometers were staggered by 45-degree angles. However, a very interesting update that has happened since 2023, when this work was happening, was that a third region in Saxony in Germany has been proposed as a site for one of the two L-shaped detectors. And this is a very much ongoing conversation. In 2026, there was a bilateral declaration of intent signed between the region of Sardinia in Italy and Saxony in Germany. And the site selection is expected to happen in 2026, so it will be a very interesting year for the Einstein Telescope, so keep an eye out for those announcements. Right, so once we had these proposed different configurations of the ET detector design, we proceeded to construct end-to-end simulations where we started with populations of Venus mergers. And for each of the Venus mergers in these populations, we injected a corresponding gravitational wave and electromagnetic signal. In particular, the electromagnetic signal were GW17017 like kilonovae. And then to each of these events, we added GW detection and parameter estimation paradigm. In particular, we used the Fisher matrix method. We used the GW-Fish library, which was developed by Jan Harms, Uliana Duplitz et al. And to each of these events, then, we attach a target of opportunity strategy to follow them up and to be able to try and detect the optical counterpart using Rubin. So what were the considerations of the TO strategy? So first, I recall this figure that you have already seen, is that we will have large number of well-localized PNS using ET, no matter which configuration of ET is selected. So we would have an order of 100 well-localized events within 100 square degrees and an order of 10 within 10 square degrees. So it's crucial that we are focusing on being able to observe as many of them as possible using as little time cost Rubin as possible. So in order to achieve this kind of large number harvesting strategy, we start with selecting only the well-localized events, which are localized better than 20, 40, and 100 square degrees. Then, out of all the events, we use a 50% duty cycle, choosing half of the events randomly to approximately account for the fact that Rubin will only observe half of the sky. We use observing strategies in G and I filters in order to capitalize on the depths of the G and I filters. So traditionally, the two filters which are used to, which are being proposed to be used for kilonova follow-up observations are G and I or G and Z. However, the I filter is slightly better depth, so we focus on having the G and I filters. And this would also capture the blue versus red color evolution of the kilonova. We observed in two epochs, so only 5 hours and 24 hours after the merger time. So in this we focused on observing the kilonova once, but on 2 consecutive nights, and captured the rapid evolution. However, we did not propose more epochs because we wanted to be able to follow up more events while minimizing the time cost for Rubin. Additionally, we explored 2 different kinds of longer exposures. So we use 600 seconds and 1800 seconds of exposures in order to be able to reach the fainter kilonova transients as many of them as possible. This is in contrast to the current observing strategies that we have for LVK and Rubin synergies, where the exposures go only up to 180 seconds. However, we decided to try and use longer exposures in order to get more events in this way. As usual, we adopted the mosaic strategy to tile the region of sky localization obtained from the GW parameter estimation. And a kilonova was declared detected if it was brighter than the 5 sigma detection limit at the time of observation in the GNI filters and in both takebooks. With this, what we obtained was, firstly, regardless of which configuration of ET we used, we found that the 600-second exposure strategy was slightly more optimal than the 1,800-second strategy. That's because the 1,800-second strategy did increase the number of detections, but came at a prohibitive time cost, Rubin. And this was something that we wanted to avoid. Comparing between the different performance of the different ET configurations, we found that looking through the lens of multi-messenger observations and joint detections, the two L-shaped interferometers of 15-kilometer arms and the triangular interferometer design with 10-kilometer arms were probably the most optimal designs, where the 12 15-kilometer arms performed slightly better than the triangle with 10-kilometer arms, and slightly is an understatement because the 12 15-kilometer arm interferometer design detected a factor of 2 more joint detections of kilonovae using the strategy that we provided. However, regardless of the configuration of ET that we end up with, what we found is that if we just follow up all the BNS, which are localized better than 40 square degrees, we would still end up with 30 to 100 joint detections of kilonovae, regardless of which ET detector design we end up having, which means that ET will be a very interesting instrument for us to be able to follow up and detect gravitational wave events with electromagnetic counterparts. Right. Another thing we concluded at the end of the study for the Einstein Telescope was that the presence of the low frequency component in the ET would be essential to detect a large number of kilonovae counterparts due to the massively improved effect it has on localizing the BNS mergers. So this is something that is crucial for electromagnetic follow-up, and we would really not want to end up with the worst case scenario where only the high frequency component of the ET is functional and we cannot access these low frequency sensitivities that have been proposed for now. Right. As I promised, I said that I would talk about two different works. So you might have guessed from my presentation so far that for this first evaluation of detector design for ET, we focused on getting rough estimates and getting overall strategies which simulate the TO we would have, but are not very detailed designs of TO strategies that we can expect to have in the next generation. So in the second part of the talk, I will talk about a more detailed study in which we explored the full plethora of perspectives of optical detections from BNS mergers, where we can really look in detail at the joint detections we can have in the third generation of GW detectors. In this work, what was different was that we focused on only the two most optimal detector designs for ET, which we can expect to be built, which are the ET triangle of 10 kilometers or the ET 2L of 15 kilometers. So we focus on these two alternate configurations. And we also studied, because we expect for ET to work in a network with other GW detectors. So we studied the impact ET would have working alone, as well as in networks with second generation and other third generation gravitational wave detectors. So this is a list of other detectors that we considered. We considered the LVKI, which is the LIGO Virgo Kagra and LIGO India, working at 0.5 sensitivity, as well as the Cosmic Explorer, where one Cosmic Explorer or two Cosmic Explorer are in function. We considered 10 years of BNS populations in order to increase our statistics and really look at the patterns that emerge over time. And we considered an optimistic and a pessimistic merger rate, giving us two different bounds, because as we know that the BNS merger rate, owing to the very few unexpected So the unexpectedly low Venus merger rate that we've observed in the last few runs of LVK has given us a very poor constraint on the Venus merger rate, and therefore this is one of the larger sources of errors for our joint detection estimates as well. In addition to that, we considered two different neutron star equations of state, the BLH and APR4, which are compatible with the GW17017 detection, as well as two different neutron star mass distributions, so a Gaussian and a uniform. And sometimes you will see these in the labels of the figures that I will present. So you might see BLH uniform, which means that that is the plot for the BLS equation state for the uniform mass distribution, and so on and so forth. So in total, we had 64 simulations in this work. And what we did was that we also improved the modeling of the kilonova light curves, where we calibrated them not only on GW17017, but also on GW190425, which, as you remember, was a Venus merger for which no electromagnetic counterpart was detected. And then to all of these considerations, we also added a more realistic target of opportunity strategy with Rubin. So when we say more realistic target of opportunity strategy, what we did was, instead of using 50% of the events randomly, now we use the exact Euclid footprint. The exact Rubin footprint. So we use the Euclid overlap footprint from Rubin Sim. It's a previous version of Rubin Sim, so you might not find this still available in the Sim. But this was from the repository of the Rubin Sim, which was created by the Rubin collaboration and by the DM team, which are working very hard on them. And we expect to have more realistic estimates from there. We account for the effect of galactic extinction on each of our kilonova light curves. And as before, we still observe in the GNI filters in two epochs. However, we assign the time of observation to each event, considering the sunrise and sunset times at the summit. And then, using all of these considerations, we declare a kilonova to be detected under two conditions. One is a more relaxed condition in which the kilonova is detected in one epoch, which means it has to be detected in both filters on one of the two nights. But in addition to that, we also have a more restrictive criteria, which is the second set of events, which we call the two epoch events, which means they have to be detected in both filters on the first night, but in at least the I filter during the second night, which is more useful in removing contaminants because it accounts for the fast evolution of the blue component of the kilonova, where the blue component might become fainter while the red component might still be detectable. To a subset of the events, we also add the optical afterglow of the gamma ray bursts. So these are calibrated to the observed rates of GRBs currently, and the optical on-axis and off-axis afterglow is attached to a fraction of the kilonova population. So we can compare the rate of detection with or without the afterglow for our kilonova counterparts. And what we get at the end of all of these simulations is this table, which gives us a total set of kilonova detections in 10 years. This is too much information, so let me guide your eye. So what I want to mention here is just using the pessimistic merger rate of PNS, and using a very small budget, so between 1.8 to 2.2% of Rubin's annual observing time, we can still get an order of 10, so between 7 to 10 joint detections per year, working with ET alone and not in a network with other detectors. However, if we go from ET working alone to ET working in a network, such as with the second generation LVKI network, it increases the rate of sky localization and gives us a huge increase in joint detections of an order of magnitude. And this can be seen here in this figure, where we start out with ET working alone and get a huge improvement jump for ET working in the network of LVKI. The improvement persists with ET working also with Cosmic Explorer. However, the improvement is not as dramatic as going from ET to ET plus LVKI. And this is because due to the natural restrictions and limitations of ground-based optical observatories, we are not able to capitalize on this much better localization given by Cosmic Explorer at high redshifts using Rubin. And what we could also obtain from this set of analysis is we could choose a certain sky localization threshold within which all events are followed up. And the figure on the left would allow us to sort of understand what time budget we need with Rubin in order to follow up all events, all PNS events within a certain sky localization and to be able to attempt to detect kilonovae counterparts for them. Looking at the efficiency of the gem detections we get as a function of redshift, in this figure, we can see the kilonova only events in the hash histograms and the kilonova plus GRBs in the transparent histograms. And as expected, what we see is that when we consider GRB afterglows along with kilonovae, we are able to reach a higher efficiency of detections, and we can reach higher redshifts additionally. And this is not surprising because also the increase in these detections that we get when we include the GRB afterglow comes from GRBs, as you can see, and it's perhaps a bit hard to see, but it's these transparent histograms at the edges on two sides. And these are from GRBs with low inclination angles up to about 15 degrees. And these are not entirely on-axis, but close to on-axis events. And therefore, it's natural that we are able to detect them with better efficiency going to higher redshifts. Another thing to notice in the efficiency is that, if you notice here in this figure, the efficiency never quite reaches 100%, even at very, very low redshifts, and drops sharply around redshift 0.3. The drop at around redshift 0.3 is quite natural. This is what we expect because at some point with the kilonova emission, we will reach a natural horizon with ground-based optical detectors beyond which they're not able to go farther and fainter, and therefore the detection rate will drop off. However, the efficiency not reaching 100% at low redshifts is due to the effect of galactic extinction. And what we see is that some events that we lose at very low redshifts are because they are intrinsically, the kilonova from these events are intrinsically faint. However, an equally appreciable number of events are being lost because of the high extinction due to our galaxy, due to the Milky Way. And these high extinction events are located along the galactic plane, as we can see in this figure. And so the effect of extinction is going to be significant for us and needs to be considered in all our simulations and projections of gem detections going forward. Right. So now we also attempt to compare what we can have with the second generation detectors, GW detectors, and their upgrades, and compare them to what we can have with ET. So what we find is that ET working alone cannot localize events as well as LVKI, and that is because LVKI, owing to the fact that it is a network, has a much higher localization capability, often outperforming the performance of ET working alone. However, when we put ET in a network with LVKI, it shows an order of magnitude improvement over all the other configurations, including the upgrades to LVKI. So here in the plots, you can see one of the labels is LVKI, which is the LEGO Virgo Kagra India, which is the second generation. And you can also see a hash, which is the upgrades proposed to LIGO after the O5 run, where we will have 3 LIGO interferometers, 2 in the US and 1 in India, functioning. So even though LVKI and a hash perform better than ET working alone, ET and LVKI together in a network can give a huge boost to these number of detections and the localization capability. However, if we take a closer look at the parameter estimation that we can have, we see that ET, even though it's not as good at localizing these events, it is, however, performing better at constraining the luminosity distances of the Venus mergers it observes compared to LVKI. And as before, ET, when in a network with LVKI, has an order of magnitude better performance compared to any of the other detectors working by themselves. And as we know, better parameter estimation gives us better joint detections. This is something that is very interesting to us. First, focusing on a subset of events localized better than 20 square degrees with ET and LVKI, we tried to see what would happen if we took these events very well localized within 20 square degrees and tried to observe them with 1,200 seconds of exposure, so twice as what we were using previously with 600 seconds. What we found is that we were allowed to reach higher redshifts using these slightly larger exposures compared to where. So you can see here the darker lines are with 1,200 seconds of exposure, and the fainter lines are with 600 seconds of exposure. So it allowed us to reach slightly higher detections. However, the increase in detections was concentrated at higher redshifts, and this would be important to determine stricter constraints for our cosmological interpretations using these joint detections. So, summarizing all of the findings, what we find is that regardless of the configuration of ET we managed to have in the third generation, ET operating alone in synergy with Rubin after the end of LSST will be capable of detecting between 10 to 100 kilonovae per year using these longer exposure strategies that I described. However, the largest uncertainty to this rate of joint detection comes from our poor understanding of the local BNS merger rate. And there are second order uncertainties which are coming from the lack of constraint of the neutron star equations of state and the mass distribution. Joint detections for ET in a network with LVKI would be an order of magnitude improvement over ET working alone. There would be an increase going from ET to Cosmic Explorer as from ET alone to ET plus LVKI to ET working with the Cosmic Explorer as well. However, the entire capacity of this increase on the GW side cannot be exploited due to the natural limitation of ground-based optical detectors like Rubin. And additionally, if we also have GRB afterglows associated with the kilonovae, the number of joint detections we will have will be much larger, and we will be able to cover higher redshifts. And these come from events with low inclination angles, so up to 15 degrees from the GRBs themselves. In addition to this, the effect of galactic extinction is crucial for the detection of kilonovae at low redshifts, and it needs to be factored into our considerations of how many joint detections we will have in the upcoming years. With that, I thank you for your attention. And these are the people who have worked on the paper and the exploration of the prospects of optical detections of BNS mergers with ET and ET networks. This is Eleonora Lofredo, Liana de Pleza, Marika Branchesi. This is a QR code of our paper. You're welcome to go check it out, or you can email me if you have any questions. And if you have them right now, I would be happy to take your questions.
Thank you. Great talk. Very exciting.
Thank you.
Okay, so we're opening the floor to questions, and I also stop recording.